Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on training a neural network. It's part of the course Analytic Methods for Lawyers, although it may be very useful to many people who are engaged in learning about how to train a neural network, whether in the Wolfram language or in others of the many frameworks that are used for doing neural network research. Now, up until this essay, I've jokingly described network training as magic, because I didn't want to go into the details. But it is now time to see through the smoke and mirrors and learn what's really going on. It's important because how you train a neural network can have a great effect on how well that neural network is capable of generalizing to new information. Moreover, by seeing how a neural network trains, you may get some idea for things that it really can't do, and why there need to be some limitations on the kind of layers that get put in to neural networks. The key phrase that you need to come out of here with is the backpropagation algorithm. There are many videos that go into gory detail and many papers and documents that go into a lot of detail with a lot of confusing notation on how backpropagation works. I don't intend to replicate that here. Rather, what I want to do is to keep things simple and to give you a good, rigorous, yet simple understanding of how it all works. Let me say this. There are a couple of things to say about this video. Most of the videos I've done for this course are, you can watch the video, you can look at the essay that goes with it, you can do both. Here, this video is really essential for the essay. It's very hard to just use text to explain backpropagation. And so my suggestion is that you look at the essay and the video together. You could just really look at the video, and I think that would be okay, but I think just looking at the essay alone is going to be challenging. And I'll confess I have struggled hard with this video because it's not a simple matter to explain how a neural network trains. If you want to look at some other resources where people have done excellent work on the subject, I'd commend you to the work of 3 Blue 1 Brown, his YouTube video channel, and Josh Starmer with his StatQuest series, also on YouTube. Let's start with some calculus. Sorry. The good news is we don't actually do any real calculus. We just use their ideas. And one of the ideas is something that you've already been exposed to in this course, which is that functions have derivatives. And those derivatives are themselves functions. So, like the function, they can be evaluated at some point. But in Wolfram language and in the real world, they can live in complete happiness as just functions before encountering any data. So it's important to distinguish between a function, which is a standalone object, and the function applied to data or evaluated at some point. That's a different thing. All right, in Wolfram language, the command to find the derivative function of a function is, drumroll, derivative. And here's how it works on a function with one argument. We're going to say derivative of 1, that means take the first derivative, and there's only one argument here, x, and this function happens to go to 2x cubed. So we can execute that, and we get back a function x that goes to 6x squared. Okay? If you don't remember how you got there, just it somehow transforms a function, and that's all you really need to know. Now, we can, as I mentioned, take a derivative function here and now evaluate it at a point. And let's see if we can figure out what that's going to be. Well, this derivative 1 of the function x goes to 2x cubed, we learned here is 6x squared. And so if we evaluate 6x squared at 3, 3 squared is 9, and 6 times 9 is 54, and so I predict this will be 54. Yay. All right, we could also take the derivative of an abstract function, a symbolic function. And Wolfram, like many other people, uses a special notation in this case, and it shows that as q prime. We can also take derivatives on functions with multiple arguments. When you do this, when you have a multi-argument function and you're taking the derivative with respect to only one of those arguments, that's called a partial derivative. Let's see how we denote that in Wolfram language. Here we've got a multi-argument function. It's of x and t, and apparently it produces 2x squared plus 5t squared. What this means, 1, 0, is I want you to take the first derivative of this function with respect to its first variable, and the 0th derivative with respect to its second argument. But the 0th derivative is always just a function, so nothing's going to happen there. So you'll see what it's going to do, and maybe we can just do it by hand. We're saying take the derivative of this function with respect to x, and if you remember anything about how to take the derivatives of polynomials, you drop the exponent down, and then you decrement the exponent by 1. So I believe, if I'm remembering my calculus from 37 years ago, 47 years ago, we won't even know. Correctly, it's 4x. So that's correct. We get a function of x and t that's 4x. Supposing we want to take the derivative with respect to the second argument, t. We just denote that as 0, 0th derivative with respect to x, and 1, first derivative with respect to t. And maybe now that you refresh yourself, you're going to realize, oh, that should be 10t. And lo and behold, it is. And just as we could evaluate a function object produced by the derivative operation at particular values, we can do this with partial derivatives as well. So here I'm going to take that partial derivative of this function with respect to x and then evaluate it at the values 2, 90,343, which I use to basically clue you in that the second argument doesn't make any difference. And again, let's see if we can do it by hand. It's saying it's 4x and x is 2, so I think this is going to be 8. And it is. All right, and here I'm going to take the partial derivative with respect to y of t and evaluate it at the point negative pi over 17. 2, again, the negative pi over 17 is a red herring, and so we learned up here that the partial derivative function is 10t, and 10t evaluated when t is 2 should be 20, and it is. Hurrah. Let's look at notation for abstract functions. And that's what, if you see this in Wolfram language code, that's what it means. And in fact, if I say, what is the input form of this? It's just going to tell me really what I gave it to begin with. So essentially, all that's happening here is there's nothing more it can do with this expression. And so it's just presenting it in what it believes to be a friendlier form. And similarly, this is going to be q of 0, 1. Okay. Instead of finding the derivative function of a function, you can find the derivative of an expression. And this way you don't have to specify the original expression as a function. So you remember our 2x squared plus 5t squared. Supposing we just saw that, it wasn't wrapped up in a function, and we wanted to find out what is the derivative of that expression with respect to the symbol x, we just use d. D is when you don't have functions. Pretty clever mnemonic. All right, and we get our 4x. How do you evaluate this expression at a value? You're going to use the /dot replace all command that we've seen. So it's take the derivative and then plug in x goes to 5. And that's all the calculus we need, more or less, for understanding backpropagation and how to train a neural network. Let's talk about composed functions. You know how I've been using this /* notation throughout this course for composed functions? There has been a method to the madness, and one of the reasons I use it is because it really fits with neural networks so well. Let's look at a composed function, and you'll see, this sort of looks like a layer diagram. There's one layer, and then there's another layer, and then there's another layer, and there's another layer, And that visual metaphor is quite apposite. That is, that's basically what composition is. It's layer upon layer of functions. So what are we doing here? The first function has a parameter attached to it, p1. So maybe the function is p1 times 3x minus y. Well, the output from that function is going to depend on p1, and so you can think of p1 as parameterizing the function. The function works differently if p1 is 5 or p1 is negative 7. All right? And then we're going to take the output from the application of f1 and p1 to some argument and apply f2 to it. And then we're going to take the output from that f2 operation and apply another parameterized function, f3 of p3, to it. And then we're going to take the output from that operation and apply another function to it, f4, but f4 takes two arguments. The first argument is going to be the output from this composition here, and the second argument is going to be some value t, which I wonder if that could stand for target. And we're going to just put that ampersand here to denote that this is a pure function, and we'll call this whole thing script capital C. Right? So there we go. All right, and you really can think of this as a neural network. You can think of f1, p1 as a linear layer with parameters p1. The function f2 doesn't have any trainable parameters, so maybe it's just some non-linearity like a ramp. It couldn't be a parametric ramp layer, though, because that does have parameters. You could think of the function f3, p3 as another linear layer with parameters p3. And finally, maybe f4 with two arguments. What have we seen? What layers have we seen with two arguments? We've seen loss layer functions, like the mean squared loss layer or the cross entropy loss layer. And so the idea is going to be, well, let's take this is our prediction, f1, f2, f3 of p3 is our prediction. Let's stuff that into the input slot here of f4 and bring in the target. Okay? So let's call the result of applying that composed function to x, which is what we start off with, our features. Let's just call that script capital L. Right? And this is just another way of writing the same thing that we saw up here. The only difference is I've actually stuffed the x in, so it's no longer a function. It's now an expression, the result of applying this function to the data point x. So what I now want to do, in order to make the visualization of this expression easier, is I'm going to show it in tree form. I showed you tree form way back when in one of the early essays videos, and we're actually going to use it now. All right, so there it is. We go up this chain, start with x, go forward to f1 of p1 of x, go forward to f2 of f1 of p1 of x, go forward to f3, p3 of f2 of f1 of p1 of x, go forward to f4, I'm going to say it, of f3, p3 of f2 of f1, p1 of x, and t. There you go. All right. Now, if we just had a conventional function and we weren't dealing with a neural network, we might throw out these intermediate values that we got along the way. We wouldn't necessarily save them. They're not useful in general. We want to know what the answer is. What is f4 of da-da-da-da-da-da and of t? But with neural networks, you want to remember, so you don't have to recalculate things. If you see f2 of f1, p1 of x in some other expression, you know, oh, wait a second, I calculated that before, and it's in memory location 37. So, in the forward propagation, in moving from layer, first layer to second layer to third layer to fourth layer, we're going to keep track of the results that we got along the way, okay? And that is crucial to the forward propagation. That's why is it forward? Because we're moving our way forward through these composed layers. We're getting so close to back propagation. But before I explain what it is, I do want to talk about the alternatives. Otherwise, you won't appreciate how really clever backpropagation is. Remember what our goal is going to be. We want to find the values of the trainable parameters in our little toy problem P1 and P3 that minimize L, our loss. And in our little toy problem, we might be able to use some conventional methods to do that. Maybe we could find a symbolic derivative of the loss function, set it equal to 0, and then use algebra to find the parameters that satisfy the equality. But that assumes that the loss function doesn't have bumps, plateaus, or discontinuities that's going to make that method problematic, and also with enough layers and enough parameters, the algebra involved, it's just going to be impossible. So, not really going to work in the real world. We could try to use some advanced numeric optimizations, such as simulated annealing, or differential evolution, or Nelder-Mead, the stuff that's sort of behind n-minimize or n-maximize that we've seen. And those are capable of coping with some poorly behaved loss functions. But even those methods really have immense difficulty where, as will frequently be the case in real neural networks, where there are thousands of parameters, or 3 years ago millions of parameters, or this past year billions of parameters. And so, if those were all the tools we had, training neural networks would be, as it was for some time, extremely difficult, which is why neural networks went through this sort of dormant period where original high hopes for them were kind of dashed, only to be revived in recent years when the genius of backpropagation became clearer. The idea of backpropagation is that when you can break down a function into a composition of little functions, then the process of finding derivatives with respect to parameters actually becomes a lot easier. And by a lot, I mean a lot. What you do is you compute the derivatives one by one in the reverse order in which the layers containing them were encountered in the original composition. You exploit the layer structure, the composition, to simplify the computation. And the reverse order is why the algorithm I'm discussing is called backpropagation. Now, I'm not positive you really need to know this, but since every other resource on the topic spends time on the chain rule, I am worried that the neural network police are going to come after me if I don't say something about the chain rule in this video, and probably they would be right to do so. So let's take a look at the derivative of a composed function. Here's my composed function, f and then g. And we'll take the first derivative of it with respect to its only argument, and we get a product. It involves two derivatives. We take the derivative of the first function and apply it to the original input, and then we multiply that by taking the derivative of the second function and applying it to the output from the first function. Okay? If we wanted to see what the actual derivative expression was, we could use d. We'll actually apply our composed function to x here and take the derivative with respect to x. And any way you slice it, you get the same thing. Really, it's the derivative function of f applied at its input x multiplied by the derivative function g applied at the output from the first function f. So let's stare at this a little bit. First of all, if either of those derivative functions are 0, then the whole thing is 0. And so, if you want your answer here not to be 0, because 0 can be a problem, you better make sure that none of the elements in the chain are 0. Moreover, if you could imagine, I know we haven't done it for Hij, Jk, etc., But if you could imagine that those end up turning out to be long products as well, then you need to be careful that these values aren't very, very small, because if I multiply enough very, very, very small numbers together, I'm going to get something really, really tiny that doesn't give me the kind of information that I might want. The other thing you can see is you don't want to throw out information along the way. Do you see how g prime, the derivative of g, gets evaluated at f of x? I don't want to have to recompute f of x. Maybe f of x is a very complicated thing. And so what instead I want to do is to store the value of f of x once it's computed, and then I can just look it up. Okay, that was it for the chain rule. Now, let's look at our composed function. And what I want to do is, remember what the last layer of it was? The last layer was, that had a trainable parameter, was f3 of p3. So let's take the derivative of our function with respect to p3. Okay, L is an expression, it's not a function, so I'm going to use d to do this. And that's going to give me something I'm going to call P3 gradient. And I'm being a little casual in using gradient and derivative. For the purposes of this video, they're essentially synonymous. All right. And we get something that looks horrifying. Good thing I told you what that meant, right? But we've got this monstrous thing here. It's actually a product again, isn't it? But I'm kind of a fan of tree form. So let's look at it in tree form. And I'm actually going to have, well, I'll show you. Let's just run this. Okay, I've got two expressions here. The one on the left is our original loss. We've seen this tree before. And this is the tree form of our derivative of L with respect to P3. This is just the tree form of this. Okay? But let's stare at this for a moment. Now, where have I seen this before? And I've seen this expression, f3 of p3 of f2 of f1 of p1 of x, right over here. And so if I were smart enough to have stored this, I don't need to do this recomputation. It's already in memory. And so I don't actually have to, oh, and where have I seen this before? f2 of f1, p1 of x. Why, I saw that on the way up here too, in the forward pass. So the forward pass resulted in memory holding most of what I need to do this computation. So this is computed, and this is computed. This is just a pure function. I don't need to know any numbers to compute it. I can just compute it once for the layer. It's just a formula, and so it doesn't, the result of the formula changes when it gets different numbers, but the formula stays the same. So I just have to compute this once. That's not so bad, and I get some function. And similarly, this derivative here, that's the derivative with respect to a layer. I can just compute that once. I don't, at the time I create the layer. And so, really what I'm doing is I'm just applying a function that I've pre-computed to some data that I've pre-computed, and I'm applying a function that I pre-computed to some data that I recomputed and some number. That's not very hard. It's like 7, so I don't have to do any computation. And then I'm just going to multiply the two together. So, although this looks horrifying, it really isn't so bad. And by being clever and storing information along the way, I greatly simplify the computation. Okay? So, now that I've found the P3 gradient, we need, let's go back and look at that formula again. Here it is. I'm going back, I did the P3 derivative. My next layer that has a trainable layer is this one, so I need next to form the derivative with respect to P1. So let's actually do that. And here's our expression. It's even more horrifying. Okay? But again, it's going to turn out to just be products. There's one product term, there's another product term, and there is yet another product term. So let's look now at the forward propagation tree form, the P3 gradient tree form, and now the new P1 tree form. Okay, so here's what we're trying to compute. Okay, and it is a little scary, but let's look at this again. Look at this. Where have we seen this before? Well, we saw it right here. And so if we just manage to save that in memory, we don't have to recompute it. We just have to look it up. And where have we seen this before? Well, we also computed that in the computation of the P3 gradient. And so again, we just look it up. So these two branches of our product are covered. What about this first branch? Well, F1P1 of x. Again, we should have computed that on the forward pass and stored it. F2 prime is just computed once. All of these pure functions here are just computed once. So it's just a matter of applying a pre-computed function to a pre-computed value. And what about F1P1 of x? Well, x sure isn't hard to compute. We know what that is. And F1 prime of P1, again, we just have to have had computed that once. And so we end up with very little work here, just looking up things in memory, and then at the end we will have to multiply it all together, but that's not too scary. And so it turns out that computing figuring out the directions in which the parameters should move is not that hard if you can decompose the function into layers and then move forward through the chain storing values and backwards through the chain in backpropagation storing values. And so the trick to the backpropagation algorithm is by doing the computations in the right order, we can substitute memory for computation and get extremely fast computation of the gradients of the loss function with respect to all the parameters. And while that might possibly, if you're very smart, seem like one of those things that's obvious in hindsight, it wasn't so obvious in front of you. There are many people, by the way, who sort of claim to have discovered the idea. There's a 1986 paper in Nature which discusses it, which possibly might be the correct discovery, but it's possible it was discovered first and sort of rediscovered or re-explained here. Well, you might be saying, so what? You know the gradient. How does that get you anywhere? Well, let's think about how you get down a mountain. Here's how I get down a mountain. I look at what is the steepest way up. I reconnoiter. And then I go in the opposite direction a little bit. So it's the reconnoiter and go in the opposite way method. And then I've gone a few feet down the mountain and I do it again. And as long as there aren't any little mini valleys or bumps, or worse, cliffs or plateaus can be a bit of an issue, but as long as it's a nice, friendly, smooth mountain, and I move slowly enough, this method should get me to the bottom. But, and so that's why knowing the derivative is very useful. You know which way to move. But how fast can you move? Like if I move like an inch every time I do this assessment, it could take me a really long time to get to the bottom of the mountain, particularly if I started kind of high. So in training a neural network, you want to figure out how fast to move. And because there could be bumps or plateaus, you don't always perhaps want to move in the opposite direction of the gradient. Sometimes you might want to move kind of in the direction of the gradient. So I now want to illustrate the process, the pathologies, and some of the cures that form the guts of neural network training. Again, I'm going to do a toy example for pedagogical purposes. In the real world, that loss function is going to be a manifold in a very high dimensional space. You know, if it's got a billion parameters, it's going to be in a billion plus one space. So even Wolfram really can't visualize billion-dimensional spaces. But we can work with curves in 2 dimensions. And while that won't give us everything we need to understand neural network training, it does give us, I think, a lot of the big picture. All right, let's generate some data. Basically, I'm just going to create some messy data where we have some x values that are spread on -3 to 3, and then some y values, some targets that are going to be from a function that's randomly chosen. So there's going to be some noise in our data. All right, and if you were curious, you could just, that's what our data looks like. Okay. And here's the model. It's the world's simplest model. No, it's not the world's simplest model, but it's a very simple model. It's alpha x, where alpha is the only parameter. There's no intercept term. So we can now calculate the mean squared error loss as a function of alpha. This is going back to our study of maximum likelihood estimates and least squares estimates. But the idea basically is we want to get an expression for the loss as a function of the parameter alpha. So how do we do that? We're going to, for each of these points, we're going to say, what is alpha of x value minus the y value? And then that's going to give us the residuals, and then we're going to take the sum of the squares of that. That'll give us the total, but we're going to divide it by the number of points. So we're not going to do power total as we've been doing all along. And we're going to use power mean. Nothing really turns on it, but the Wolfram loss layers are the mean squared error loss measure, not the total squared error loss measure. And so in order to keep the analogy, I decided to use the wonderful power mean function instead of the wonderful power total function. All right, so we're going to get our expression for the mean squared error. There it is. So it's some kind of quadratic. And let's plot it as alpha goes from 0 to 4, and indeed we get a lovely parabola. So, you know, we can sit here in our infinite wisdom and know that really we should try to be heading for making alpha 2, but of course our neural network doesn't know that. If it knew that, we wouldn't be using a neural network. So let's do the following. Let's initialize our first guess. Where I'm going to put me at 3.5, coordinate 3.5. You can think of that as latitude 3.5, and go up our mountain. And let's figure out what the derivative is of our loss function, this thingy here, evaluated at, well, first of all, let's just figure out what the derivative is symbolically. So that's the function that gives us the derivative. And so if we are at 3.5, and I really need to do this. There's a flaw in the code here, isn't there? I really need to show what is grad evaluated at 3.5. It's saying it's a positive number, so that suggests that I need to move in a negative direction, which is of course correct, in order to get to the bottom of the mountain. But how far do I move? Do I move like this far? Do I move this far? How far? So I'm going to move 1/10 of the amount of the derivative function. And so I'm going to write a function that moves me. We're going to start with an initial guess for the parameter, a learning rate of 0.1. You remember learning rates from gradient boosted trees? Well, they're back. And here's our derivative function. And so our new parameter value is our old parameter minus, because we're going in the opposite direction, the learning rate multiplied by that gradient or derivative function evaluated at the old parameter. So there's our function, and now let's compute what the new parameter should be, and let's just do it by hand before I evaluate this code. Well, let's see. Our derivative was 10.64, and 1/10 of that is about 1.06, and 3.5 minus 1.06 is 2.44, I think. So let's see if I did that correctly. And indeed, thankfully, I did. Okay, so now let's just do that over and over again. For example, what if I said, what is new parameter of grad of that? And it would tell me, oh, that's 2.12. And what is new parameter of grad of that? And it would tell me that's 2.03. So I could just keep doing that over and over and over again and hope for the best. There is a Mathematica function, a Wolfram language function that does this. It's called fixed point list. And the idea is, it's like nest list. You just keep iterating over and over and over again. And the only difference from nest list is instead of saying, I want you to really do it a certain number of times, you put a bound on it. You say, don't do it more than 500 times, because bad stuff can happen when you keep iterating a function. Moreover, if you want, you can say, hey, let me know when you think the numbers are sufficiently similar that you want me to stop. And I'm just going to say, look, if the numbers differ by less than 1 part in 100 million, that's close enough for me. All right, so let's actually run fixed point list on our new parameter function starting at 3.5 on the mountain. And it looks like we converge at very, very close to 2. And it took us 18 iterations to get there. All right, well, good. But maybe if we changed the learning rate, we could get there faster. Maybe I was taking baby steps, and I should have been taking banana steps. So I've changed the learning rate here to 0.15. Everything else is the same. And yeah, I got there in 9 steps. Great. Well, if banana steps are good, maybe giant steps are even better. Let's increase the learning rate to, oh, I don't know, 0.285 and run that. And, it's taken 501 steps, so I bumped up against my abort cutoff, and it looks to me like it's blowing up. It's oscillating back and forth and getting bigger and bigger and bigger. So what happened? How did this happen? What happened was I moved so far in the negative direction that the absolute value of the derivative at the new point was higher than it was at the old point. And so then I had to move in the opposite direction an even greater amount. But now the absolute value of the derivative at the new point is even bigger than it was at the new point. And I move in the opposite direction in an even bigger amount. And so the system just explodes if the learning rate is too high. And in fact, in this instance, you actually can use algebra to figure out what that critical value is where it explodes. The test is whether the absolute value of the gradient is smaller than the absolute value of the gradient evaluated at the new parameter value. And so I'm going to find out for what value of nu, the learning rate, will that circumstance occur? And it turns out it occurs when nu is greater than 0.2829, which might coincidentally be why I picked 0.285 here. And so what this is telling us is that there is some optimal learning rate that results in the system not blowing up, but also getting there swiftly. And an awful lot of the effort of advanced neural network training is trying to figure out what that optimal learning rate is and potentially adapting those initial guesses based on what it finds about the loss function as training proceeds. A video footnote before I proceed further. Turns out you really don't have to move according to some multiple of the gradient. And there are a lot of algorithms that have been developed that use things like the sign of the gradient and other factors to determine how far to move. And my guess is that we're going to come up with some better methods than this simple multiple of the gradient. And in fact, there are better methods now, but yet better methods. This is where a fair amount of research goes in neural network training, because neural networks are clearly incredibly powerful. And so the faster and better you can train them, that's worth a ton of money. And so I suspect we're going to, when I make the sequel to this video in 5 years or whatever, I'll be talking about something else. All right, let's look at two pathologies that can really make gradient descent miserable. The first is the local valley, and the second is the vanishing gradient. So to see the local valley problem, let's make a loss function that has lots of local valleys. I'm just going to superimpose a little sine wave on top of our parabolic loss function. All right, so we can see lots of little valleys. Now, n minimize, that function we've seen before, is actually smart enough to figure out how to deal with a function like this. I believe that is actually the global minimum, but I could make this worse, and I could put it in enough dimensions that even n minimize would not get to the right answer. So let's see how we use modified gradient descent to get to the bottom, or if we can. First, we'll do exactly what we did before. We're going to form the derivative function of the loss function. Here's our loss function. Let's compute the derivative. There we go. There's some sort of weird trigonometric thingy-bob going on here that I don't remember, but I will assume that Wolfram has correctly figured out the derivative. And now this is the same code. It's just the only thing that's different is I'm using grad v instead of grad to iterate the new parameters. Otherwise, it is the same. This is the 1 in 100 million thing. Oh, the only other thing I'm using here, we haven't seen this before, is I've given augmented terse an optional argument. Normally, it just shows you the dimensions of your data, but you have the option of doing something else, and I wanted to make a plot of the data. All right, so what do we see? We see chaos. We see the stock market here. Or Brownian motion or something, where it's just jumping all over the place. And this has to do with basically it jumping in and out of valleys. And it doesn't seem to be converging to the right answer within any reasonable time. Well, you might think, well, maybe you just need to go more slowly. So let's decrease the learning rate down to 0.01. This is the Sansa-Stark learning rate. That didn't work either. It just gets trapped in the valley and goes back and forth and back and forth. And so that's not good. What we really need is sort of the same idea that actually simulated annealing relies on, which is to introduce some randomness into all of this. And maybe instead of moving in proportion as a multiple of the gradient, what we should do is we should draw from a distribution centered at the gradient and then multiply that by our learning rate, and that's how much we move. So that distribution could actually have a negative value. You could actually get a negative value, and therefore you would move in the same direction as the gradient. So I've slightly embellished our new parameter function here to add a second argument to this first grouping here, which says draw from a distribution that depends on the value of the gradient and use that to figure out how much to move. I've set a default value here. This is always going to produce 1, and so the default behavior is to just not have any randomness at all, but it's going to give me the potential to introduce randomness. What you really need to understand is that I've managed to introduce randomness into the movement of the parameters. So let's see how that works if my movement is drawn from a distribution centered at the gradient value and with a standard deviation that has some relationship to the gradient value. Let's see if that works. Well, it gives me an answer. Let's see if that introduction of randomness improves anything. And the answer is it's not great. And so what this is telling us is that where you have a bumpy function, you're going to need to be pretty sophisticated in figuring out how to get to the bottom. And truth be told, you may never actually quite get to the bottom. Hopefully you will get close. All right. Next pathology is the vanishing gradient. Let's look at another loss function. This one doesn't have any valleys, but it does have a big mesa, a plateau. This is the crevasse here. So we'll compute the gradient of it, and we're going to run our new parameter algorithm on grad 0. Everything else is exactly the same. And, it stopped. It just went like one turn, and then the process stopped. Why did it stop? It stopped because at 3.5, the gradient's 0. And if I move a multiple of the gradient, I'm not moving at all. And so I just get stuck there. This is the vanishing gradient problem. And remember I told you, you could get a vanishing gradient if any of those products in that whole chain rule thing were 0. And so what you need to be in designing a neural network is to be very careful that you shouldn't have situations where the gradient is very likely to be 0 for any of the layers. By the way, does it help if I add some randomness? Here's my, I thought maybe that would help. And I haven't been clever enough in my randomness. We've still got the stock market here going up and down. So what this all means is that if you get answers out of a neural network, but the person has not trained it properly and has subjected themselves to either local valleys or to vanishing gradients, then the answer that the neural network gives is not going to be very good. The good news is that if you're careful, there's a whole industry of computer scientists working on this problem, and the odds of you're getting a really bad answer using a professional package are much less than they might have been a few years back. Time to discuss batching. All right. Here's the question. You've got data coming into your neural network. How often do you actually adjust the gradient? We could use what's called full batch. That is, you run all the data through the neural network, you compute the average gradient for each of those data points, and you move according to the average. And actually, if there are fewer than the rule of thumb is maybe 10,000 records in a data set, full batching may work pretty well. And in fact, we're going to see it does work pretty well on my data that I'm going to have. But if you've got more than 10,000 records, or if you've got a large amount of data and you have a big neural network, then you're not going to be able to fit all that data in memory. And so you really can't use full batching. So you're going to have to come up with an alternative, like partial batching. And the polar opposite of full batching is what's called stochastic gradient descent, often abbreviated as SGD. And here, we sure avoid memory problems. We just move after every point. So that's good. Moreover, sometimes you have weird fits of the data, and so your computation of the gradients is going to be kind of weird, but that's good because it could get you out of local valleys. Remember, sometimes we might want to move in the wrong direction to get out of the valley. So stochastic gradient descent tends to explore a large space of possibilities for the parameters. Is there anything bad? Yes, there are things that are bad about stochastic gradient descent. First, if you've got outliers, you could move the parameters in a really bad way, and the network could sort of lose its way in the course of trying to get to the bottom. Second, the way computers work, they like to do all these operations in parallel, and so if you're just feeding it one piece of data at a time, it's computationally inefficient. Now, there are all sorts of algorithms that try to make sure that SGD works well, and so when you hear things like momentum or atom or rprop or RMSprop or a host of others, those are basically all detailed ways of trying to make sure that stochastic gradient descent works well. There's a compromise, and this is what generally tends to be used, which is mini batches. You don't move after every data point, but you also don't try to clog up your computer with every single data point at once. So maybe you shove 100 data points at the computer, and then you average up the gradients, and then you move in the direction opposite the mean gradient. So you get some randomness depending on what the batch contains, but it's sort of smoothed out like an outlier. If it's got 100 other pieces of data, it shouldn't have that much of an effect. The other thing you're going to want to do probably is shuffle the data each time you get through a whole round of it so that it's not always seeing the same batch. And the principles of Atom and RMS prop and the rest of the gang work on batching as mini batching as well. All right, so your reward for having endured all this is you get to watch neural network training in action. So I'm going to create a little baby network here, simplified syntax. Hopefully you're able to translate this by now. Linear layer of 3, element-wise layer ramp, compressor down to 1. I'm going to give it 2 pieces of input. There's our input. Blows it up to 3, ramps it, stays at 3, compresses it down to 1. All right, I'm going to make some synthetic data. I don't think you need to know that code. And now I'm going to start with stochastic gradient descent and see what that looks like. To visualize what's going on, I've written a function called progress. There it is. It's kind of complicated, and I don't think you need to understand it. The one thing it does make use of, though, is something called a radial axis plot, which the rest of the world calls a radar plot or a spider plot. There are a lot of names for it, but let's look at it. Okay. The idea is I've got high dimensional data. I've got 6-dimensional data here. How do you visualize 6 dimensions? And the answer is you make 1, 2, 3, 4, 5, 6 slices of pie, and you show the value as you sort of move around this clock face. So this is 2, 6, 11, -3, 1, and 9. Okay? And so if we have lots of weights, we could use a radar plot to show all the weights at once. Isn't that cool? At this point, you may notice 2 things. The first is that I've changed the resolution of the screen. What I'm about to do doesn't really fit easily in the Camtasia window, and so I've reduced the magnification. The second is I noticed a little bug or a way I could actually do this better in presenting the material, and so I've made a little change in the code, which will be reflected in the posted notebook. All right, what's all this code? This code is to visualize the progress of the neural net. I don't feel you really need to understand it at any level of detail. I will sort of illustrate it as we go along. I'm going to initialize 2 global things of data, which are going to help in that visualization. Again, I don't think you need to know the details. What else? We're about to train our network. Here's our features, here's our target. We're going to start with stochastic gradient descent as our method. I'm just going to run it for 50 rounds. It's going to turn out that's probably adequate anyway. I'm going to run a batch size of mini batches of 64, learning rate of 0.001, that's our friend new, and here's what we're going to report, and we're going to report after every round. Okay, so with that introduction, let's watch what happens as we train. All right, and you can see here is the current weights. You can see the loss is decreasing as we move along. This is the change in the weights vector since the last round, and this is the gradients. This is how it's sort of poking around. You can also see the learning rate declining. This is something that SGD does. It tends to decrease the learning rate as we move forward. As we're getting 64% done, you can see that our weights have pretty much stabilized, and our change in the weights is almost a perfect circle at 0. Still poking around with that gradient, looking for something, but we're not really finding it, and that learning rate is diving, and we're done. Okay, so that's stochastic gradient descent. Let's see how our friend Atom works. Everything's the same except for the method. Let me make sure I reinitialize stuff. Get rid of the run where I forgot to reinitialize. And we're off. Okay, you can see the weights are pretty stable. We've almost pretty quickly gotten to almost a perfect circle where the weights don't change much. Our gradients are still high. They're running around. And you'll also see that in Atom, you start off with a low learning rate and tend to move upwards. These numbers are the ratio of the current learning rate to the initial learning rate that I specified. And so you are seeing some changes here in the weights, but pretty much we're done. I guess that's what you need to see on training. The other experiment that I want to do is to see if batching matters. And so basically what I'm going to try is one instance at a time. This is pure stochastic gradient descent. Then I'm going to try mini batching with a size 64, and then I'll try full batching where I use the entire training set, the length of the training set, as the batch size. And in each instance, I'm going to evaluate the R squared to see whether batching affects performance. I'm going to run each of these for 20 seconds. I might, well, let's just start running, okay? All right, here we go. And we're off. Batch size of 1. It is getting some progress. It's bumpy because each time it hits a new data point, it's sort of readjusting that gradient. So if there's noise in the data, which there is, there's going to be a little bit of noise in our gradient descent process. But as I've indicated, that's not always bad. We're done, and we got a 0.92. I must say, I think that's higher than I've gotten in my experiments. Let's see if we can beat 0.92. All right, let's go to the mini batch size 64. Go mini batch. And look at that diving loss rate. It's smoothed out because with mini batching, if you have some outlying data, it tends to be balanced off by other data. So keep chugging away. And let's see what we get, trying to beat 0.92. Well, not by much. All right, let's see if full batch does any better. Okay, we've set it to the length of the feature training data, which is the whole shebang. All right, it's diving, going down nice and smooth because it's being fed all the data at once. And let's see how it can do. Seems to have pretty much stabilized. And 0.921. So at least on this data today, and there is an element of randomness here, I didn't make much difference how I batched. I will say in the past, I have done better with bigger batches, but that's the way the network crumbles. All right, so I kind of feel like trying to learn neural network training in an hour or so is like trying to learn constitutional law in that time frame. So you just have to hit the major concepts and highlights. And this is a complicated area for computer scientists and mathematicians, but advances in the field, as I indicated, are really worth billions of dollars, not to mention saving the planet, because training these neural networks actually consumes immense amounts of electricity. So what you should understand, though, is just as we saw in earlier lessons that the architecture of the neural network can greatly affect its results, that's also true with training methodology. I wish I had a better instance for you here, but you're going to have to trust me that many times issues like batching does make a big difference. And so lack of success in a neural network could just be an artifact of the training method used and might not be robust. So when you're confronted with data from a neural network or a model from a neural network, it's important to see how robust that predictions are to changes in stuff like the change in architecture or the change in method of training, the batch size, the time to train, the criteria for stopping training, details that I haven't gone into of how Atom and SGD and its friends work. The bottom line, though, is that a smart data scientist can manipulate the results of neural network training just as they can manipulate the results of statistics. And one of my hopes is that you, as astute understanders of neural networks, will be able to question the methods that are used and understand what was done. Thanks.